Hey, welcome back everybody. This is Pre-Calculus Day 9. We're going to be talking about inverse functions. And before we start, I want to show you that you've already been sort of inverting or reversing processes for a long time. So for example, if I take a number and I add 2, well, I can reverse this process and get back to 5 by subtracting 2. So I could also take 7 and reverse this process to get back to 5. So in some sense, we've got this reversing or inverse process here. I could also take some number. Let's say I take 10, and let's say I double it. Well, if I want to reverse this process to get back to the starting value of 10, I would do the opposite, and I would divide by 2. And so these reverse processes are important because they allow us to solve equations. And the big question right now would be, okay, well, we can do these for numbers, right? We can reverse a process for numbers. Even think of exponents and roots, right? But what about functions? How do I reverse a function? Also important because that's going to be valuable for solving equations. So let's look at the following. So let's say we've got a couple sets here. And let's say I've got some element x, and I want to send it over here via some function f. So let's say after I apply f to x, it lands somewhere at this value, f of x. What if I want to reverse the process and go home? Sort of in some sense reverse the arrow. So what if I want to go from here, here? Well, that's what the inverse function is going to do for us. Let's for now call it g. So this reverses the process. It brings me back home. And so the observation I want to make right now is the following. G of f of x is equal to x. Now, if that happens for all x's in the domain of f, then we would say that g is the inverse of f, sort of the reversing function. Let's actually say that. So if g of f of x equals x, let's be careful and say for all x in the domain of f, our starting function, for all x in the domain of f, and we have the following. So say this happens for all x's in the domain of g, that would be the starting function, the inside function. Then we say that f and g are inverses of each other. And in this case, we would say that f and g are invertible. And so one big question we're going to want to investigate is, well, when is the inverse mapping actually a function? Okay, so let's get a corresponding theorem. We're going to have a lot of technical theorems to work out, but it'll be worth it. We'll get a strong theory of inverses through this. Okay, so corresponding theorem. So I'm going to say, suppose f and g are invertible functions. So we're going to get a whole list of things. So the first thing is, well, the range of f is the domain of G. Remember, the range is the set of all outputs. So the range of f is the domain of G. And also, well, the domain of f is the range of G. Maybe that's not so surprising. So think about the story that we had before. So I just showed this on one element. Of course, there could be several. So there was x. We brought it over here via some map f. And so when I reverse the arrows via G, we want to notice something. So in this case, since G is taking elements from here and sending them there via some rule, this is the domain of G, right? Think about the direction of the arrows. Well, this domain of G is the range of f. And then look over here. Well, your starting values for f are here. So this is the domain of f, but that's exactly, follow the arrows, the range of G. So this statement isn't too far-fetched. Okay, so not so bad. And so we get another statement as promised in this theorem. So f of a equals b if and only if, well, before I give the result, the punchline here, let's think about this. F takes A to B. What can you say about G, the reverse map? Where does G take B? It takes it to A, because if G and F are invertible, they do the reverse things. If F takes A to B, G takes B back to A. Okay, again, not surprising. Say there's A. Maybe there's B. F of A equals B. And then G of B equals A. So 3 I'm going to star because this is actually leads to an important realization. So before I write this, let's make an observation. That's an input and that's an output. This specifically tells me that the ordered pair A, B is on the graph of F. What does this tell you about ordered pairs? Well, this tells me that the ordered pair B, comma A is on the graph of G, and we're going to make a connection with that in a moment. So let's say this for now. So AB is on the graph of F. If and only if BA is on the graph of G. Okay, so before I expand on this, maybe I want to note something. What does if and only if mean in mathematics? I think that's worth noting. So if I have two statements, let's say this is statement P, f of A equals B. Let's call that statement P. And let's say I've got another statement Q, G of B equals A. We'll call that Q. So if and only if means the following. So we'd say P if and only if Q. So that's what we have, P if and only if Q means two things are holding. So it means if this happens, then this. So that conditional holds. If P, then Q. So if this happens, I'm guaranteed this under the assumption they're inverses. But I also have the reverse implication. So I need and is important here. So and. And if Q, then P. So that's what if and only if means. It means if this happens, I'm guaranteed this. And also, if this happens, I'm guaranteed this. Again, under my assumption they're inverses. So anytime in math you hear if and only if, it's implying this biconditional. Okay, that was worth it. Okay, so what does this mean here? So if AB is on the graph of F, then we have BA is on the graph of G, and if BA is on the graph of G, then AB is on the graph of F. Well, think about these 2 points. These are reflections through what line? Y equals X. So let's note that. So property 3 tells us graphs of inverses are reflections about y equals x. Very, very important idea. And let's investigate this. Let's look at this idea geometrically. Okay, so we're going to look at a function and its inverse. We're going to look at both of their graphs, and the point of this is we're going to observe that they really are reflections through the line y equals x. So I'll call this a little investigation. And these are just 2 lines. So let's graph f of x equals 3x plus 4. Remember, that's the same thing as y equals 3x plus 4. Should remind you of a line in y equals mx plus b form. And let's also graph g of x equals x minus 4 over 3. And I'll be able to see pretty quickly that these 2 graphs are inverses of each other. Okay, so I'm going to save a little time. We know how to graph lines. If I were to graph both of these lines, I'd have the following. So right here, this is the graph of the line f of x equals 3x plus 4. Right? It's got a slope of 3, a y-intercept of 4. So that's f of x. This right here, this is the graph of g of x. Now, g of x is equal to x minus 4 over 3. So notice that these 2 lines are reflections through the line y equals x. So here is y equals x. And because these 2 graphs are reflections through y equals x, well, they're inverses of each other. Notice that if, so let's take this point, this is 1 minus 1, make that a little bit darker. Notice if this point AB is on the graph of G, then BA, right? So switch them, BA is on the graph of F. So yeah, if these 2 are really inverses of each other, if the point AB is on one of the graphs, then the point BA will be on the inverse. And that's where the reflection through y equals x is coming from. If that property holds, that's exactly the definition of a reflection through y equals x. Okay, so you can say here, if AB is on the graph of F, then BA is on the graph of G. And I could keep picking points like that. Right? So if AB is on G, then BA is on F. And if I were to fold along this line, you would see that this would match up with this would correspond with this, etc. And so this is what graphs of inverses look like. Reflections through y equals x. Okay, so from here we get another technical theorem. So first, let's suppose that f is an invertible function. So 1, there is exactly 1. Inverse function for f, so inverses are unique. And we denote this in the following way. And I have to speak a little bit about this notation with function inverses. And this is read f inverse. So this is a little bit of an abuse of notation that we often do in mathematics. We recycle. Sometimes it's confusing to new learners, and I can understand why. So this refers to the function inverse. This is not 1 over f to the first. So we're not using exponent notation in the typical way. It's just a notation to denote inverses. So context really matters. If you see this in the context of functions, then you understand it to be an inverse. If you see this in the context of numbers, then you're talking about a reciprocal. So be careful. So context is important. Okay, so with functions, I understand that this is not an exponent in the typical sense. This is just notation denoting the inverse. Interesting. So given a function that's invertible, its inverse is unique. There's not 10 inverses for it. There's just one unique inverse. Well, that's helpful. And we're going to just note something that we observed earlier. The graph of y equals f inverse of x is the reflection of the graph of y equals f of x through the line y equals x. Okay, cool. So we've introduced a bit of notation. We know the inverses are unique, and we know what the graph looks like. You just take the original graph, you reflect it through this line, and now you have the graph of the inverse function. Okay, so now a big question is there a way to test if functions are invertible? I mean, how do I know? Are all functions invertible? It turns out no, all functions are not invertible, and we do have a way to test, and that's what we want to talk about now. So how to test if a function has an inverse or is invertible. I'm going to star this because it's so important. So I'm going to say a function f is said to be one-to-one or sort of a synonym for one-to-one is injective. So I'm going to say a function f is said to be one-to-one or injective if and only if whenever we have this equality of outputs, we must have equality of inputs. So you might want to stop and pause and think about, and maybe sketch a graph or something. Think about what a statement says. So yeah, whenever I have equal y values, essentially, that came from the same x value. Another way to say this is, or if given unique inputs, so separate places on the x-axis, then we always have unique outputs. So order matters here. And that's for all C and D in the domain. Both of those are for all C and D in the domain. Domain of F. And so how do I interpret such a statement? Let's actually write this down sort of verbally. So unique, so not equal means unique. Unique inputs always lead to unique outputs. Okay, so a function is one-to-one if it has this property. For new learners, this is probably, again, these two are actually, this and this are actually equivalent. This might be easier for someone to think of. Unique inputs lead to unique outputs, or suppose I had equal outputs, it must have came from the same input. Okay, well, from this, we get a theorem, and this is called the horizontal line test. So it says the following. So a function is one-to-one or injective if and only if every horizontal line intersects the graph at most one time or once. Okay, so we're going to continue with a follow-up theorem, and then we're going to apply all this. And then we're going to see how all this ties into testing for inverses, and then subsequently finding inverses. So this theorem is all about equivalent conditions for invertibility. And so it says the following. So suppose f is a function. The following statements are equivalent. So 1, f is invertible. That's equivalent to statement 2, which says f is 1-to-1 or injective. And that's equivalent to statement 3. The graph of f passes the horizontal line test. So I'm going to write that and then sort of talk about how to interpret a statement of the form the following are equivalent, or a theorem of the form the following are equivalent. Okay, so how do such theorems work in math? They work in the following way. So whenever you see the following are equivalent, as soon as I know one of the statements is true, the other two follow. If I want to think about that as a sequence of conditionals, let's say it's statement 1, 2, and 3, I have 1 implies 2. What that means is if I can show that 1 is true, then I'm guaranteed that 2 is true. Since they're all equivalent, that also means that if 2, then statement 1 is true. So if f is 1-to-1, then f is invertible. Okay, well that's true. It also turns out if I know statement 1 is true, then that implies that statement 3 is true. If I know that statement 3 is true, that implies 1. But I actually get more. So 1 implies 3, 3 implies 1. 1 implies 2, 2 implies 1. 2 implies 3, 3 implies 1. So I also get that that's true. So if I know that 2 is true, then I know that 3 is true as a consequence. And also, if I know that 3 is true, then I know that 2 is true. But even more than that, if I know that 3 is true, then I know that 1 is true. So it's sort of like a buy one, get two free. The moment I know one of these statements is true, it implies the other two. So it's like, say I had to, if they asked you, hypothetically, prove that f is invertible, it's enough to show it's 1-to-1. Or it's enough to show that the graph of f passes the horizontal line test. Okay, so the following are equivalent means you have exactly the sort of chain of logic. Sometimes we write it like this in a more succinct way. 1 implies 2. 2 implies 3. I don't write that. But 3 implies 2, etc. So yeah, as soon as I know one of these, I know that the other are true. They follow as a consequence of knowing one of them. If you take a course called linear algebra, there's a list of over 30 statements with one of these. So it's like a buy one, get 29 plus free. It's really, really useful. Okay, so let's now test for invertibility. I can test if a function is invertible just by checking if it's 1-to-1. So if I can show that a function's 1-to-1 using the definition, that will prove if it's invertible or not. Okay, so let's practice the 1-to-1 skill, and then we'll practice invertibility. So determine if the following functions are 1-to-1 in 2 ways. So we're going to determine 2 different ways if the following functions are 1-to-1 or not. Okay, so let's say we have the following. So our first function f of x is 1 minus 2x over 5. Our second function g of x is equal to 2x over 1 minus x. Our third function h of x is x squared minus 2x plus 4. And our last function is given as a set, and that's perfectly fine. Okay, so I think we should go about this. Let's check the horizontal line test, because I think that's going to be a good opportunity for me to show you sort of the shortcomings of the test. So check the horizontal line test. Sometimes it's great, sometimes you'll see. And then B, use the definition of one-to-one. So how about use, there we go, the definition of injectivity, or one-to-one. I know it's enough to check one of these because of the previous theorem. Remember, that was the buy one get two free. But I want to show you how to do either of these tests. Okay, both of these things will test for invertibility of the function. Okay, that's the point of using these tests. Okay, so let's look at the graph of this. Hopefully you recognize that as a line, right, with slope minus 2/5. And okay, so first using the horizontal line test. So here is the graph of f. And the observation I want to make is, for any horizontal line I draw, notice that it intersects the graph at most once. So say I draw, I don't know, this. So it intersects at most once. And it has to be for any line I draw, right? I can't just skip a bad point in theory. But you'll notice, yeah, for any horizontal line I draw, that horizontal line intersects the graph at most once. When I say at most, what does that mean? It means no more than one time. So it intersects either 0 times or 1 time at most. Okay, so this certainly passes the horizontal line test, because every horizontal line that I draw, or every horizontal line one could draw, intersects the graph at most once. That's letting me know that the function is one-to-one and thus invertible. Since this passes the horizontal line test, again, I know it's one-to-one, and we care about one-to-one functions because they're invertible. They have inverses. Okay, we're going to come back to this when we test for one-to-one, sort of the definition way. Okay, so let's look at the graph of G, and we can play the same game of horizontal line test. So here's the graph of G, and exactly here is where I can point out sort of the difficulty in using the horizontal line test to concretely determine invertibility. Now here it's easy, right? You can clearly tell that I'm intersecting the graph at most once. All the way down, horizontal lines intersect the graph at most once. That's good. But here maybe it's a little bit trickier because of how subtle or small the slope is here. I can't really tell if is that all one horizontal line and this is intersecting it at a bunch of different places. So this exactly points out, so it's hard to tell. I mean, the slope might be so subtle that a horizontal line will intersect at most once, but I can't see it the way it's drawn. So I would say that the horizontal line test might be a bit inconclusive. This sort of hints at why we need formality and why we need the formal algebraic definition. That's going to tell us more concretely what's going on here. So yeah, our own sort of senses fail us. It's too subtle to tell, too difficult to tell. Okay, let's look at the graph of h. Does this pass the horizontal line test for invertibility? No, look at that. Look at that. I mean, just because this is nice in one place, right, at the vertex, that's not enough to say it passes the horizontal line test. Does every horizontal line I draw intersect at most once? No way. Look at these two intersection points on that horizontal line. I mean, here, look at these two intersection points on that horizontal line. So this fails. The horizontal line test. That tells me that the graph is not one-to-one, and that tells me that the inverse wouldn't be a function. There might be some relation that's an inverse relation, but because this fails the horizontal line test and is not one-to-one, its inverse would not be a function. Now, what about this? What does this graph look like? Well, the graph is just three isolated points, and that's fine. We can have functions like that. Nothing wrong with that. It doesn't have to be given by some equation or rule like that. So here is the graph of f. But notice, these 2 points live on the line y equals 1. So this actually fails the horizontal line test. This is not one-to-one. So I know that its inverse wouldn't be a function. Okay, so we looked at this under the lens of the horizontal line test, but what about using the definition of one-to-one to determine invertibility? I actually think that's much stronger than the horizontal line test. Okay, so let's look at this using the definition of one-to-one. So we're going to test for invertibility by checking if this is one-to-one. So remember, we want to check for all C and D in the domain of f. If f of C equals f of D, then we must have C equals D. That's our test for one-to-oneness. Okay, so that's the test. And so we just follow it through. So we're going to assume that f of C equals f of D. And we're going to show as a consequence of that assumption that C equals D. Again, that's sufficient to prove that this is a one-to-one or injective function. So what is f of C? It's exactly this function evaluated at x equals C. And what is f of D? It's exactly this function evaluated at x equals D. Okay, we can multiply both sides by 5. That gives us the following. Then we could subtract 1 from both sides. And then, of course, divide both sides by -2. And that's the result we wanted. That proves that f is one-to-one. And that's an important thing to know because that tells me that its inverse is indeed a function. So what would happen if this was not invertible? I wouldn't get a single C equals D. There might be more down here. Remember, It might even be stronger to provide a counterexample. I'll show you that in a few moments. But that's how you prove that a function is one-to-one. Much stronger than looking at a graph because our senses fail us, but the algebra does not. Okay, so let's test the next function g. Let's test and see if g was one-to-one. Remember, that was the one where it was hard to tell. I couldn't tell if it passed the horizontal line test or not. So let's see what happens with the algebra. And we're going to test it using the definition of one-to-one. Okay, so let's assume that g of c equals g of d. So what is g of c? It's exactly our function evaluated at x equals c. So that gives me 2c over 1 minus c. And so similarly, g of d is 2d over 1 minus d. Now I can get rid of the 2. We can just take a half of both sides. That's fine to do. And so if I wanted to solve further, of course I could cross multiply. That's what we're going to do to proceed. We're going to cross multiply. So if I've got two ratios, then this product, of course, always equals this product, assuming we're not dividing by 0 or not, because we're only considering c and d in the domain. So this product is equal to this product. Okay, cross multiplication. I'll just distribute on both sides. So I've got c minus cd equals d minus cd. And I can add cd to both sides, and that gives me c equals d. Cool, so the algebra speaks loudly. This is a one-to-one function. Couldn't tell from the picture. How powerful. The power of algebra. Okay, so I'll say therefore g of x is one-to-one and thus invertible. How cool. I mean, that picture was confusing, wasn't it? I couldn't tell. Now h of x, so let's take a look at the picture. So h of x was the parabola, if you remember. So that was the third one, the third function we looked at. So for h of x, we had the following. So this fails the horizontal line test. So this is definitely not one-to-one. And so the inverse is not a function, right? So what does that mean? How can I prove that this is not one-to-one? So in a sense, so just note, just recall, right? F of x or h of x, whatever you want to call the function, is one-to-one if, this is for all c and d of the domain. So how do I prove that it's not one-to-one? I need to find a counterexample. So how to disprove? So I'm going to say to show f is not one-to-one, we need the following. So this and the opposite of our conclusion hold for some instead of for all, for some. C and D in the domain. Okay, so this is sort of how to show f is not 1-to-1. So we need these equal y values, but they come from separate x values. So think about this, right? This should make sense if I bring up the picture. So equal y values, that's, so for example, let's keep it simple. Say right here, because these are nice values. So equal, actually there's better. That's fine. So equal y values, yeah, the better ones to choose would be right there, but that's fine. Equal y values. So f of c, that y value, equals f of d. However, they came from different locations. So instead of being 1-to-1, let's say here's c, and let's see whatever x value corresponds to that is d. And again, they're at the same y location, so f of c equals f of d. So the same y value didn't come from the same x value. So instead of being 1-to-1, I've got 2-to-1, right? So way to think about this is c and d map via h to the same y value. So that's actually 2-to-1. Do you see that? C and D both map to the same y value. This is the same y value, same number. So what's an easy location that happens? Maybe if y is 4, right? 1, 2, 3, 4. So let's use this and this right here. So the observation I want to make is that, so specifically f of 0 equals f of, looks like 2, right? F of 2. So that's 1, that's 2, 3, 4, 5. And that y value, so for right here, that y value looks like 4. So f of 0, so here's the observation we want to make. Let's organize this. So the observation is that f of 0, that's this y value, so f of 0 is 4, and f of 2, both equal 4. And we can compute that directly, right? So f of 0 is equal to 0 squared minus 2 times 0 plus 4, which is 4. And, well, not f of h of. H of 0 is 4, and h of 2, that's equal to 2 squared minus 2 times 2 plus 4, but that's also 4. So maybe I want to say h of 0. So this is real life here. These mistakes are real. Genuine mistakes, just for you. But they're both equal to 4, that's the point. However, 0 is not equal to 2. So unique x values here and here mapped to the same y value. So therefore the function's not 1-to-1. It's 2-to-1. So since h of x is not 1-to-1, h of x does not have a function inverse. Let's try, just before we try the last one, just to clarify, let's try another one real quick that's not invertible. Just to keep it super, super clear. So just like a quick side example. So consider we have f of x equals the absolute value of x, right? Notice that f of -5 equals f of 5, right? That's true because the absolute value of -5 is equal to the absolute value of 5, which equals 5. However, -5 is not equal to 5. Therefore, f of x equals absolute x is not 1-to-1. Okay, so I hope that makes sense. Yeah, two different x values map to the same y value. That's not 1-to-1. Okay, and so the last one that was the set, just to get back on target here. So how can we show using our definition that this is not 1-to-1? So let's do it right here. So let's note f of -1 equals 1, and f of 2 also equals 1. Right, same output for both of these inputs. Right, they're both equal to 1. Yet -1 is not the same as 2. Therefore, f is not 1-to-1. Okay, and you can see that in this case that was 2-to-1. So that's not 1-to-1. Okay, great. So now we've got a way to test if functions are 1-to-1, and that's important because that will tell us if the function has an inverse function or not. So with that said, let's actually practice finding the inverse. So we know how to test and see if the inverse exists, but how do we find that inverse? So finally, how to find an inverse. So we say steps for finding the inverse of a 1-to-1 function. And specifically a 1-to-1 function that's in y equals f of x, or y equals g of x, or y equals h of x notation. Step 1. Write y equals f of x. So what do I mean by that? So what I mean is, say they gave us f of x equals x over x plus 2. I want to write that as y equals f of x. That's what I mean by this. So given this, write it like this. So step 1, write y equals f of x. It may be given as y. If the function's not given as y, call it y. Well, remember a function and its inverse are reflections over y equals x. What does a reflection over y equals x do? It interchanges the x and the y value. So step 2 is interchange x and y. Why? Because the reflection over y equals x that occurs with inverses. So next we want to solve. So now you're going to have x equals f of y after you interchange, and you want to solve that for y to obtain y equals f inverse of x. And then you want to check by performing composition of functions. So check by computing f after f inverse of x. And you're hoping to get x out. And then f inverse after f of x. And again, you're hoping to get x out of both. Okay, so if you recall, so going back, let's see here. So going back, we proved that f and g were both 1-to-1. Since both f and g were 1 to 1, that means that they have inverse functions. So let's use these as examples to find inverse. Let's find the inverse of f first, and then we'll check. And then we'll find the inverse of g and check. And we're going to use our steps. Okay, so for example, we already proved that f of x is 1 to 1. Let's find the inverse. And verify. Okay, so step 1, we were given f of x equals 1 minus 2x over 5. Remember, step 1, call that f, y equals f of x, so y equals f of x. 2, interchange. X and y. So that means we're going to have x equals, again, that's because of the reflection through y equals x that occurs with inverses. So we've got x equals 1 minus 2y over 5. Okay, and then 3, we want to solve algebraically for y. Then write the inverse. Okay, so that's not too bad to solve, right? So to solve this, well, we've got 2 equal ratios if we put that over 1, so we can just cross multiply. So that gives me that 5x is equal to 1 minus 2y. I can subtract 1, so 5x minus 1 is equal to minus 2y. And then I could just divide both sides by minus 2. So if I divide both sides by minus 2, so the minus is going to change both of those signs. That's going to give me y, but that's what we're calling f inverse. So what we're claiming is the inverse is exactly this. And we're going to prove that this is indeed the inverse of f. Before we do that, interesting thing I want to note is because of this interchanging that comes from the reflection through y equals x, what you're going to notice through enough work with these is that the domain of f, I think we mentioned this earlier, we did. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. There's always that switching because of the inputs and the outputs switching. Okay, so we've got this so far. We now want to check. And we check by computing two things. F after f inverse of x. We want to show that's equal to x. What does that mean? They're inverses. They neutralize each other and you get the starting element. That's why we want this. And then also the reverse composition, that f inverse after f of x yields x. So yeah, this sequence of maps gets me back to the starting element. That's what we want to show. And really, by keeping x general, we're saying this happens, I should be a little bit more specific. This happens for all x's in the domain of what's my starting f inverse. And then here, for all x's in the domain of f. Okay, so let's go for it. And for my sake, let's just note that f of x is 1 minus 2x over 5. And we said that what we're claiming is f inverse. We're about to prove that it really is. is we said that f inverse was 1 minus 5x. Now, don't always think that these two just interchange. We do have to go through the algebra. Okay, so the first thing we want to compute is, so f after f inverse of x. How do I compute that? That's exactly f of f inverse of x. But what do I mean by this? It means that I apply the f function after I apply the f inverse function to x. Okay, so this is exactly this. And how do I interpret this composition? Well, just go to f, and everywhere f has an x, I evaluate it at 1 minus 5x over 2. So there's an x right there. So I'm going to see a copy of this in for x. So that's 1 minus 2 times that whole quantity. Over 5. So this one in for x, everything else looks the same, 1 minus 2 and 5. Okay, we're going to work that out. Did you catch it? Did you catch it? Look right here. Mistake of the day. There it is. That should be a 2. I had a 5 there. Okay, so we fixed that. Let's go ahead and cancel the 2's out. So we've got 1 minus 5x over 5. And then just distribute the minus 1. So, share the negativity here. It's minus 1 plus 5x over 5. But that's exactly 5x over 5. And that's exactly x. So that's good. We wanted that to happen. Okay, and now we're going to just check the reverse composition. And this is how we prove that what we're claiming is f inverse truly is the inverse function of f. Alright, so now checking the reverse composition. So 2, we want to check that f inverse after f of x, we want to show that that gives me x. But what do I mean by this? So that's f inverse of f of x. So you can see what I mean. I keep referring to this as like a sequence of maps or a sequence of functions. So it's like you take some element x, you apply the f function. That's like the first chain in your sequence. And then after that, you apply the f inverse function. Okay, so how do I compute this? It's f inverse of, well, f is this. So it's 1 minus 2x over 5. How do I interpret this? I go to the function, and then everywhere I see an x, I plug in a copy of this. Hopefully correctly, fingers crossed. So 1 minus 5 times, well, this is playing the role of our x, all over 2. Okay, so yeah, that went in for that. Okay, so the 5's will cancel. So we've got 1 minus 1 plus 2x over 2. So that's 2x over 2, and that's x. That's what we want. So the functions are inverse. And their inverses, you can see that in a sense neutralizes. And that's going to be important down the road for solving equations, right? If I've got some object trapped inside of a function, I need the inverse to undo that to get at the object inside. Okay, as promised, let's try this for g. Okay, so next, recall. So g of x is exactly 2x over 1 minus x. So we're going to use that 4-step process. Step 1 is to write y equals g of x. So y equals g of x. Step 2 is to interchange x and y. That, again, is because of the reflection over y equals x. And then 3, I want to solve algebraically for y. So again, I'm going to cross multiply. So this product equals this product. Put over 1 if you have to. So this product equals this product. And then how do I solve for y? Well, you just want to bring all the y terms to one side and then solve. So maybe I'll bring all the y sides to the right. It's your choice, really. So bringing all the y terms to the same side. And then I can solve just by factoring out a y. Don't forget you can do that. Factor out a y. And then divide. So that means that x over 2 plus x is equal to y. And that's what we want to call or claim is G inverse. Okay, so yeah, right, y equals g of x, so y equals g of x. Interchange x and y, solve algebraically for y. That's what we're claiming is the inverse, and then we prove it's the inverse. And I think for step 4, so now we show that the order doesn't matter as long as we do them, we cover both compositions. G after g of x is x, and then g after g inverse. Okay, so g inverse after g of x is x, and g after g inverse of x is x. Okay, so let's do this first. Again, the order doesn't matter, just as long as both of these are computed. Okay, so we're saying we want to compute g inverse after g of x. So what do we mean by this? That's g inverse of g of x. And so now we're just going to refer to these two. So that'll be g inverse of, now g of x goes in here. And then I go to g, what I'm claiming is the inverse, g inverse. And then everywhere it has an x, here and here, I plug in this. Yes, even if it makes a compound fraction. So it's good. It builds your math grit, right? Lots of algebra. Okay, so yeah, we've got a complex fraction. We want to get rid of that complex fraction. So let's go ahead and multiply the top and the bottom by this quantity over itself. So let's multiply by 1 minus x, let's say over 1, over itself. Why do we do that? That's going to help us get rid of the complex fraction, the fractions within fractions. Okay, so for the top, these will cancel. I'm left with 2x. Downstairs, now you need to remember this gets distributed to both. So I'm going to have 2 times 1 minus x from this distribution. And then here, this will cancel with this, leaving me with 2x. So just distribute the 2. So that gives me 2x over 2 minus 2x plus 2x. But that's exactly 2x over 2, and that's exactly x. That's what we want. So I'm feeling pretty good about this. Okay, so next we just check the reverse composition. Okay, so for the reverse composition, we've got g after g inverse of x, but that's exactly g of g inverse of x. And what do we say? G inverse we're claiming is x over 2 plus x. That's going to go in for g everywhere that g has an x. So you're going to see a copy of this plugged in here and here. So that's exactly 2 times, that's our input, over 1 minus our input. And really, we're going to do the same thing. We're just going to get rid of the complex fractions. So we're going to multiply by 2 plus x over itself. And note these will cancel up top, leaving me with 2x. And then remember to distribute both downstairs. So downstairs I'm going to have 1 times 2 plus x here. Minus these will cancel, that's going to be x. The x's will cancel, so that gives me 2x over x, which is exactly x. Therefore, I mean exactly what we claimed. This function is the inverse function of g of x equals 2x over 1 minus x. So really practice this. Super important skill. We're going to apply this, just to give you a heads up. So we're going to apply this when we start talking about exponentials and logarithms. That's going to be huge. And then, of course, when we talk about trigonometry and we define the inverse functions and we want to solve trig equations, this is going to be a hugely important idea. It never stops being important in math, so you want to really nail the skill.